Good morning. Today's lesson we were looking at theories of flight, and I'm hoping that you've watched those videos and you might have an understanding now of the difficulties of expressing how lift is generated by a wing in a qualitative way. Like I said, engineers have a great handle on how wings are designed and how aircraft are designed using very complex equations and modelling. They can model airflow by a computer. I think it's the acronym is CFM. Correct me if I'm wrong about that. But you can model flow with a computer. You can also I've sanitized my hands, so I'm not going to get COVID. You can also use the Navier Stokes calculations, okay, equations. So, but that's all very complex. So when someone says, well, how is lift generated? Like I said, there's two theories. Classic theory, which involves Bernoulli's principle, which used to rely on the equal transit argument, which is actually incorrect. The idea that the wind is flowing over the top and the two particles have to arrive at the same time. Sort of a weird take on quantum entanglement, which doesn't happen with air particles. So we actually know from wind tunnel testing, which is one of the videos that I gave you, that top flow, if you have a particle arriving at the big, if this is your wing and your particles arrive at the same time, this top particle is actually going to flow faster. It's going to arrive at the end of the wing before this bottom particle. So it's actually flowing much faster, which is why we have lift generated. So it is obeying Bernoulli's principle. So if you want to write about the classic principle, you're going to need to talk about Bernoulli's principle, or you should talk about Bernoulli's principle. But equal transit, we know it's a dumb idea, so we're not going to use it when we try to use a classic model. Okay, so I would say it's a good idea to be able to draw a diagram and a brief description. Okay, so think about what's happening and say, so for the classic lift theory, and with classic lift theory we're talking about Bernoulli's principle, which is also what we talk about when we talk about a Venturi and other such things. Okay, so classic theory, utilizing Bernoulli's principle, you would say if a wing is traveling at an appropriate angle of attack and speed, then the airflow over the top is faster than the airflow underneath. This means we have higher pressure on the bottom of the wing and the top. And you could write brackets according to Bernoulli's principle. And if you wanted to be a real nerd, you could write there, underneath there, the total pressure, which is a constant, is equal to dynamic plus static pressure, okay? But that will be enough, okay? So faster airflow, lower static pressure. And then for your diagram, what I suggest would be a really good thing to do is for the classic model, they normally draw an airfoil that's that shape. Okay, and then you can just draw airflow coming up over the top, airflow going straight underneath. Okay, and then you might write under here, underneath the bottom, higher pressure, and on top you could write lower pressure, and we could draw a little arrow up and write lift. Actually, your center of lift is going to be somewhere. It's just lift is distributed across the whole aerofoil. Okay, it's a distributed force, but you'd probably be better off putting lift here, an arrow that says lift. Okay, and you could write up here in brackets faster flow and slower flow. Now, we've talked about in the videos as a qualitative solution to the problem, that is not the best explanation, because it's just saying we got faster flow on top. Well, it's not really telling you why, is it? So we can see that there is issues with this explanation, but it's an explanation nonetheless, a simple one. You have faster flow on top, slower flow underneath, as evidenced by your wind tunnel video, and that explains why the lift happens. Okay, kind of doesn't explain why the faster flow is on top, which is the problem. But anyway, that is your Bernoulli's classic explanation. Pause the video, copy the diagram, copy the explanation, and then think about how you would write that explanation again. It doesn't have to be exactly in those words, but you need to talk about faster flow on top, lower flow underneath, and the difference in pressure which creates that lift. Okay? Mention Bernoulli's principle, classic principle of flight, the classic theory of flight. We're going to mention Bernoulli's principle. Okay, so that's that theory, and then so we'll call that theory, because in Copeland they say it's theory number 1. Okay, and it's the one that used to be taught most often when I did basic aeronautical engineering, knowledge. I was never an engineer. That was the theory that was taught if you were a pilot. Okay. Theory number 2 is the flow turning theory. So you might write up here flow turning, and this is the airflow that's flowing over the wing, and in brackets underneath the physical principle that's put into play when you're talking about that particular theory is Newton's third law. Okay, Newton's third law, which states for every action there's an equal and opposite reaction. Okay, so the lift is generated as a reaction force to the flow that turns as it travels over a wing or an aerofoil that has an angle of attack that's appropriate. So once again, we can start our definition in a similar way as this definition. That way we marry the two and we've got less to remember. Okay, so we can say if a wing, you could say aerofoil as well, but let's just say wing. If a wing is traveling at an appropriate angle of attack and speed, then the airflow over and under it is forced to turn. okay? Forced to turn, that's why it's called flow turning, okay? As a reaction to the force causing this flow turn, inverted commas, we have a force generated which is our lift force. Okay, and then in brackets you can say, according to Newton's third law. Okay, so that is your flow turning according to Newton's third law. Okay, diagram for that. I find that for this particular diagram, you're better off using your more standard shape. It doesn't need to be so cambered. Okay, it's at an angle of attack. You can see there's a little angle there of attack. So for our airflow underneath comes to the wing and it has to turn. Now over the top, like I said in the videos, that's a little bit harder to explain. Okay, so we have, obviously these are all parallel, and then when they come over here, the flow is turning. Okay, so we can write up here, there's a force acting down, and we can say F causes such a mess. F causing flow turn, and then we can put a little arrow going up, equal and opposite really, and we can say lift force as reaction to flow turn force. Okay, so that lift force, the one that's going up, is a reaction to the one that's causing the flow turn. Okay, so they're your two definitions of lift. Okay, the classic and the flow turn definition. Okay, that didn't take that long, or it did actually, it took 13 minutes, but there was a lot of time spent explaining. Okay, so you should be able to now rattle off a definition of lift, a qualitative rather than a quantitative definition. Understanding, of course, like we discussed, each of these explanations, if you're a very questioning sort of person, is going to immediately raise quite a few questions, okay? So really, a marriage of these two would be great, but it's very hard to do that. So that's why we still have usually these two models that are wheeled out when someone's trying to explain how lift is generated. If you talk to a physicist about this subject, it's quite in depth. Anyway, like all things, it's it's not as simple as you'd like it to be. Pause the video, take notes, do the diagrams, and really, if you've got a diagram, if you remember a diagram, and you can use your powers of description, you can think about what's happening in the diagram. You can say airflow arriving at the wing is turning. okay? Turning is caused by a force, reaction force is lift, okay? So you've got that definition in the diagram. You don't have to remember all these words, okay? It's not about remembering all the words, it's about defining it. So wing traveling at appropriate speed, appropriate angle of attack, diagram tells you what's happening. This one here, we have wing traveling at the appropriate speed and angle of attack, and we have airflow over the top, which is faster. We've written faster flow, lower pressure, slower flow, higher pressure. Okay, so that diagram can tell you what you need to do to define what happens for the classic theory of lift. Okay, wing traveling at the appropriate speed and angle of attack has higher pressure, slower flow and higher pressure underneath, and faster flow and lower pressure on top. This pressure difference generates lift. Okay, two definitions. Hopefully that helps. I'm assuming that you managed to get through all of that by yourself, but if you didn't, you need to write those definitions down. Okay, they could be useful for you, in future, maybe in your HSC. Bye.